Okay, so let's write down Gauss's law. The integral of the electric field over a closed surface is equal to the charge that's inside, or the charge enclosed, divided by a number, epsilon naught. And what we want to do is show in a very simple example how to use this to find the electric field. So notice that if we want to use this expression to find the electric field E needs to come out of the integral sign, because on the left-hand side, E is under the integral sign. So that tells us that the electric field must be everywhere the same on this surface, this closed surface, right? Because that's what that circle indicates. So we need to look at the way the charge is distributed and figure out what kind, where in space, a two-dimensional region of space where the electric field is everywhere the same, so that we can take this expression, the left-hand side, and turn it into E times the integral just of the surface area to get the surface area. Okay, so notice that we went from vector expressions here in a dot product to just an expression without a dot product, and so these are magnitudes. So we no longer put an arrow on the vectors at that point. So, and the right hand side, of course, is just Q enclosed over epsilon naught. So let's just show using an electric field that we're familiar with how Gauss's law works. So let's consider a point particle of charge, I don't know, capital Q. Okay, so we have a particle of charge big Q located in space, and we want to find the electric field using Gauss's law. Now we already know from experiment that the electric field is simply K times the value of the charge, which in this case is capital Q, over the distance squared times r hat, right? So if we're not dealing with the xy plane only, and we're thinking three-dimensional space, then that's a perfectly reasonable expression for the electric field. Okay, let's start to use the K constant as 1 over 4 pi epsilon naught, and turn this electric field into Q over 4 pi epsilon naught r squared times r hat, the radial unit vector. Okay, so we want to show how Gauss's law can get us this electric field. Well, the left-hand side requires thinking of a closed surface, so where is the electric field everywhere the same? Well, at some distance r, right? So let's say this is a distance r. The electric field here has the same magnitude as it does everywhere that's a distance r from the point particle, and that is a sphere, right? So I can't draw a sphere, I can draw the cross section of the sphere on this sheet of paper. Okay, so this is some sphere of radius r, where r can be just a variable. So really we're dealing with an infinite collection of spheres of radius, of radial values that are greater than 0 and less than or equal to infinity. Right, so they go from 0 all the way to infinity. Okay, so what does the left-hand side reduce to? Well, let's go up here and recognize that on that surface, the electric field is everywhere the same, so we pretend not to know its magnitude. Well, we end up here, so the left-hand side looks like E times just the integral over the surface, and then we look inside and we find how much charge there is. Well, all the charges inside is just big Q. So in this case, the right-hand side is big Q over epsilon naught, and the left-hand side then becomes E times the surface area. Right, we're integrating the electric field on this surface, and we get the surface area, which is 4 pi r squared, and that's equal to Q, capital Q over epsilon naught. And so this gives us the magnitude of the electric field, because we turned vectors via the dot product into a scalar, and so these are the magnitudes. We get E in magnitude is equal to Q over 4 pi epsilon naught r squared, and we then turn it back into a vector by putting an arrow on the E and associating a unit vector with this magnitude. And we know, because we applied Gauss's law, that the electric field must be radial. That's why we chose the sphere. And so via Gauss's law, we can, of course, derive what we already knew, which is this.